Hi there, we'll be continuing our work with graphing trig functions by hand. In our last lesson, we were graphing y equals the sine of x. And we noticed that it's this wavy curve that just oscillates between -1 and 1, and it just continues forever. We figured out what our graph looks like by making a table of ordered pairs. Our x-coordinate is our angle in radian measure. Our y-coordinate is what is the sine of that angle. And then we plotted our points and we just connected with a smooth curve. So we did not discuss, but it might be a good idea to discuss that the domain of the sine function is all real numbers. We know that the number pi, for instance, is a real number. It's irrational, but it has a value. It's 3.14. So 2 pi would be about 6.28. So the domain is all real numbers. Now the range, on the other hand, is what are the y values for y equals sine of x. The range is going to be from -1 less than or equal to y is less than or equal to 1. So that's the domain and range of our sine curve. We noticed that for our sine curve, what we didn't talk about but might be a good idea to mention is if I look at just one period of the sine curve from 0 to 2 pi, this is what the sine curve looks like. It starts here in the middle, see, and it ends in the middle. Okay, and what we're interested in is what do all of the different trig functions look like. So let's move on to cosine, and then we'll compare and contrast it to the sine. All right, cosine. We know that cosine is the first coordinate. We have 0 radians here, pi over 2, pi, 3 pi over 2, 4 pi over 2 if you want, 5 pi over 2, 6 pi over 2, etc. So let's go ahead and with a text box, let's figure out what is the y value at each of these x values. So the cosine of 0 is 1, right? Because it's the first coordinate. The cosine of pi over 2 is 0. The cosine of pi is -1. And what about the cosine of 3 pi over 2? That would be 0. And I'm just going pi over 2 increments around, okay? So the cosine of 2 pi would be 1. The cosine of 5 pi over 2 would be 0. The cosine of 3 pi is -1. So I have some ordered pairs, and I have created this graph for you. If this wasn't here for you, it's easy enough to do an XY kind of axes. Your y, the biggest it'll be is 1, the smallest it'll be is -1. And along your x, if we're counting by pi over 2s, I just hopped over 2 and made a dash, hopped over 2 more and made a dash. Now let's grab our pencil tool, and we probably could size it, I don't know, right around there. And we want to plot the point 0, 1. So 0, 1 is right about there. Oh, and I think I wanted to use purple. So yeah, so 0, 1. Then pi over 2, 0 is here. Pi, -1. 3 pi over 2, 0. 2 pi, 1. 5 pi over 2, 0. And I'm realizing if I put a dot here, it wouldn't make sense. So I look up at my table and I realize that I missed that the number 3 pi, if this is 1 pi, 2 pi, 3 pi, the cosine of 3 pi is actually -1. So good thing we're always thinking, is what I'm going to do in this graph going to make sense? And if not, where did I go wrong? So 3 pi, -1 is down here. This looks better. And you see that it's oscillating, just like the sine curve did. So I'm expecting that this value is -pi over 2. Let's check. What's the cosine of -pi over 2? Well, here's -pi over 2. Cosine is 0. Cosine of negative pi is negative 1. Cosine of negative 3 pi over 2 is 0. And the cosine of negative 2 pi is 1. So excellent. I can see that there's going to be a pattern. Everything is feeling right to my eyes in terms of expecting patterns. And what I'm going to do is I'm going to start at 0. And instead of drawing straight line through, because it's not linear, I'm going to kind of curve it the way I would a polynomial function. And it changes right here to concave up, changes here to concave down, do you see? And this is the way the cosine curve looks. And it's going to lift around right there. If you don't like your curve, you can undo that last piece and it will fix for you. So there's that. Now I'm going to go in the other direction. Not loving that. Easier for me to go to the right than the left. Definitely not an easy thing to do. So don't worry if you're having a hard time with it. It's even harder on Pear Deck than it is with a pencil. See how I'm just not happy with it? Don't worry, I'm not going to make you suffer watching me do this. I'm going to go with this one and call it a day. Not perfect, but there it is. Okay. Wow, that kind of looks identical to the sine curve to me, doesn't it to you? Doesn't it kind of look like it's, if we could say congruent, doesn't it look like it? Let's look back at the sine curve. It's this up and down motion, right? But I focused on this period from 0 to 2 pi on my sine curve. So let's do that with the cosine curve as well. Let me grab my line and my yellow and let's do the same thing from 0 to 2 pi. And let's just kind of box this in like I have, you ever see old-fashioned viewfinders when you're just zooming in with your eyes on one little area here. This is what I'm looking at. And now all of a sudden the curves don't look the same, do they? Let's look back at the sine. Let's look at the cosine. What has happened? Can you see there's a shift? Can you see that what the sine curve, it's almost like the cosine started here at pi, see it at pi over, it's almost like the cosine starts high and ends high. So just be aware of these little nuances of the curve, okay? But I think that the domain and range are going to be the same. I could even copy and paste them. Why not? I'm going to do that. So my domain and my range are still the same, even though it's the cosine and not the sine. So there's your cosine curve. Looking good. Now this is when it's just the parent cosine curve of y equals cosine x. Just for a minute, take a trip down memory lane with me, okay? For a quick second, do you want to remember with me y equals x squared? Remember our parent quadratic function? And do you remember when we had y equals x squared and we graphed it, what the graph looked like? The graph started here, and then remember, because the leading coefficient was 1, I went over 1 and up 1, over 1 and up 3. You remember all this. And then you could absolutely connect these dots, right? And you'd get your parent quadratic function. This is just your general quadratic function. Now, what would happen if instead of y equals x squared, what would happen if I had y equals 3x squared? Well, then we knew that this would be a shift. Instead of over 1 up 1, it would be over 1 up 3 times the steepness, if you will, as the typical parent quadratic function. What if I had this? Y equals x minus 2 quantity squared. That would mean I shift this curve 2 to the right All right, so all of this to say that all the work we did earlier with quadratics, you're going to be doing something similar with trig functions. So eventually you're going to be able to make a prediction. What do you think this would look like? In fact, let me ask you that right now. What would be the difference between y equals cosine x and y equals 2 times the cosine of x? Hey, remember when we had y equals negative x squared? What did that do to the graph? Remember when there was a negative sign out in front? Changed the concavity? What would y equal negative cosine of x do? So you're going to take your prior knowledge from these other functions, and you're going to try to extend that and apply it to trig functions. All right, so we're going to go on to one more. We're going to do the tangent together. You ready? This one could be a little bit tricky. Here we go. This could be tricky. All right. Well, the good news is we're going to use the pi over 4 family. Why is that the good news, Miss Miles? Because tangent is sine over cosine. And in the pi over 4 family, you've gone to the right and up exactly the same number of units. And any number over itself is 1. So how beautiful. I kind of love that. So we're going to go ahead, and everywhere you see a dot, we're going to figure, and I'm going to make my dot a little bit thicker. Everywhere we see a dot, we're going to find the tangent at that spot, okay? And we're going to write that value into the table. You ready? Remember, tangent, sine over cosine. In other words, your y coordinate over your x coordinate. All right, let's grab a text tool. All right, let's go. What is the tangent of 0? Well, look at your 0. We've got 0 for the y and 1 for the x. Sine over cosine, 0 over 1 is 0. I can handle that. Not bad. What about the tangent of pi over 2? All right, well, it's going to be sine over cosine. Can I divide by 0? That is undefined. That is meaningless. So this, my friends, is going to be a place where the tangent curve is undefined. And we need to understand what that means. Again, we're using your prior knowledge of that, vertical asymptotes. Let's go on to pi. So I guess I'm hopping over pi over 4 right now, and I'm going to pi. All right. And the tangent of pi is 0 over negative 1 or 0. Okay, I got that. And I'm going to make a prediction. This next one's going to be undefined. Let's see. Negative 1 divided by 0 is, in fact, undefined. All right, now we're going to go to 2 pi. And the value of 2 pi is the same thing as 0, right? 2 pi around the circle is the same thing as 0 around the circle. So the tangent of 2 pi is also 0. Now let's get some fun coordinates in here. Let's do pi over 4. All right, sine over cosine. That has to be 1. I like that. 3 pi over 4. Well, this is pi over 4. You can think of this as 2 pi over 4. Here's your 3 pi over 4. Sine over cosine is just negative 1. 5 pi over 4. It's going to be down here. Sine over cosine, they're both negative, so the tangent is positive. And then 7 pi over 4, sine over cosine, that's going to be negative 1. So this is really nice. I've got a whole bunch of things I can do to get me ready to graph this this tangent curve. First thing I want to do is I'm paying attention to these undefined places. And from my prior knowledge with graphing rational functions, remember denominator, when you divide by 0, you get what's called a vertical asymptote. These are the undefined places of x. So at x equals, and by the way, this is x, right? And this is y. At x equals pi over 2, I have a vertical line that the curve will approach but never quite reach. And I like to make a dotted line. So with my eraser, just put a couple of erasures so it looks like a dotted line. Now I have another y asymptote at another vertical asymptote at 3 pi over 2. So here we go. 3 pi. Oh, I wasn't on my right tool. At 3 pi over 2. Okay, there it is. And with my eraser, I can make this dotted. Okay, so remember with rational functions, whenever you had an asymptote, this would go something like, it could go like this, remember? Or remember, it could go something like this. So what we want to do is we want to use the other points in the tangent graph to figure out how this would go. But I also want to observe that the tangent of negative pi over 2 would also be undefined. So I'm going to go ahead and graph that now. I think it's going to help me. And you do the same thing, okay? And I'm thinking the tangent of negative 3 pi over 2 is also undefined, because you can just spot patterns again in math and extend what seems to make sense and prove your guess by going, what's negative 3 pi over 2? Oh, it's here. Is the tangent really undefined? Yeah, 1 divided by 0 is undefined. Okay, great. Now let's look at these points. Let's grab our pencil tool, pick a color that you like. I'll do the darker red. And on my sizing, I gotta bring it up just a tad. All right, 2 pi comma 0. That's right here. Pi over 4. Oh, let's go 0, 0. Let's do that. I forgot I hadn't graphed these points. Pi comma 0. Oh, look at this. 2 pi comma 0. So let's go backwards. You want to? So the tangent of pi or 2 pi or negative pi, these will all be 0, right? Can you see that? All right, now let's look at the pi over 4. Pi over 4 comma 1. Now, where is pi over 4 on your x-axis? It's halfway to pi over 2, right? So you want to go pi over 4, 1, just like this. Then you want to go 3 pi over 4, which is here, negative 1. You want to do 5 pi over 4, 1, and 7 pi over 4, negative 1. And this pattern is, I can see that it's kind of making sense to me. It looks like in every panel, shall we say, it kind of looks like there's 3 dots in a row like this. So I'm going to guess that there's going to be another dot here. I'm going to guess that there's a dot down here. And I'm going to guess that this pattern just continues in each, we'll call it panel, okay? Which is just an interval. All right, now what's nice is we are going to graph our tangent. And it is not a linear function. We're not going to connect dots. Instead, we're going to remember about asymptotes. How do we deal with asymptotes? Well, it means this is going to continue towards it, but never quite reach it. So there must be a place here where the graph just twists around, you see? So each of your tangent functions, I kind of like the way the tangent looks. They all kind of look like this. In a way, it's like a tessellation. It's like just the same pattern, just pushed over, translated over. See it? This is how the tangent looks. Now wait, I'm wondering, why am I going up like that with my arrow? Maybe I shouldn't go up like that with my arrow. Let's think about this. Would there ever be something greater than 1? Well, I think there probably would be. If this is pi over 4, and this is pi over 2, pi over 3 would be between them, right? Somewhere between them, 1/3 of the way to pi. Pi over 3 is something like this. Let's think about the tangent of pi over 3, because I want to make sure it makes sense to connect and extend through. All right, tangent of pi over 3, well here, pi over 3 is 60 degrees. The cosine of 60 degrees is 1/2. The sine of 60 degrees is the square root of 3 over 2. So what's the tangent of pi over 3? The square root of 3. What is the square root of 3? Oh, it's definitely more than 1. So it does make sense that we're going to do this, okay, and connect our dots this way. Now, like always, I definitely didn't like that. Like always, we like to use Desmos as a way of checking that our work makes sense. And what I need to really get this good is I need a vertical asymptote here. That'll help me. All right, so this is a pretty good sketch. I think it's not too bad. So there we go. All right, now we're going to go ahead to Desmos and we're going to graph this, okay, you guys? All right, let's do it. Y equals tangent of x. Ready? F of x equals. Now, before I type it in, let's make a prediction. I've got I've got a 0 at pi and 2 pi and 0 and negative pi. I have vertical asymptotes at pi over 2. Well, listen, if pi is about 3.14, pi over 2, 3 divided by 2 would be around 1.5. So I'm going to see this graph is heading toward 1.5. Okay, let's check. Ooh, look. Look. So I'm going to do a vertical line at pi over 2. I'm going to say x equals, I'm going to just type pi. That's how you do it on Desmos. There's pi over 2. There's my vertical asymptote. And I can even make it a dotted line, which is super cool. I think there's another vertical asymptote at negative pi over 2. Stick with green, and I'll make it dotted again. There's another vertical asymptote here at 3 pi over 2. And hopefully you feel like, yeah, things are starting to make sense with graphing trig functions by hand. All right, now let me ask you this question. Can I stretch this? Can I make it steeper? I mean, it's about yay steep. Looks like it's kind of like the lattice point is kind of going over one and up one. What if I put a 2 in front of tangent of x? Would it go over 1 and up 2? Let's see. It did. So see, these are things that you can play with the function. Anyway, nice spending time together.